In this video we're going to look at the process of choosing suitable probability models for discrete random variables. Now, in the course of M2 we met 3 discrete random variables, and we'll start by having a recap of these random variables. There's the discrete uniform distribution, the binomial distribution, and the Poisson distribution. And at this stage, what I'd like you just to do is to pause the video and read through the slide carefully to remind yourself about when you can use the 3 different distributions. Okay, for our first example then, we've got the mountain rescue team in a mountainous area of Wales is called out at an average rate of 1.2 call-outs per day during the month of September. Highlighting any assumptions that need to be made suggests a suitable probability model for the number of call-outs that will be made during the 7-day period of the 3rd of September to the 9th of September next year, and use the model to predict the probability that there will be more than 10 call-outs during the period. So, if we let x equal the number of call-outs during 7 days of September, then, provided we make the assumption that call-outs occur one at a time and are independent of each other, and that they occur at this average but random rate of 1.2 call-outs per day, then we're in a position where we can apply the Poisson probability model, and with a 7-day period and an average rate of 1.2 call-outs per day, then we would be expecting 8.4 call-outs during the course of the week. So we would be using the Poisson distribution with lambda equals 8.4. The probability that x is greater than 10, that there are more than 10 call-outs, is 1 minus the probability that the number of call-outs is less than or equal to 10. And we can work out the probability that x is less than or equal to 10 using our calculator, using the Poisson distribution on our calculator. And the probability that x is less than or equal to 10, if x is Poisson 8.4, is 0.7743, so our required probability is 1 minus 0.7743, in other words 0.2257. Final part of the question says explain with reasons whether this model could be applied to the number of call-outs this rescue team will receive during a week in December next year. Now there's all sorts of limitations here. You've got fewer people out on the mountains probably in December than there will be in September. The weather is very different in December than it is in September. So much so that it may even lead to the fact that multiple call-outs could happen at one time if the weather was really bad. So, quite frankly, you've just got to think of 1 or possibly 2 reasons why you think December and September really aren't going to be comparable for the call-out at a mountain rescue service. For our second problem, we have Gail preparing for a multiple choice test in which there will be 50 questions, each with 5 possible answers. She declares that she's got a confident knowledge of 85% of the material to be tested, but knows nothing about the remainder of the material. For the questions that she has confidence about, she reckons she has a 90% chance of answering that question correctly, but she also realises that she will just have to guess the answer to questions about which she knows nothing. By drawing a tree diagram or otherwise, we've got to determine the probability that she answers the question correctly on the paper and the probability that she had to guess the answer given that she answered it correctly. Now we'll try part 1 first of all by drawing the tree diagram. So the tree diagram, we've got a given question. There's a chance that she's got confident knowledge of that question or that she's no knowledge of that question, and then in each case we've then got the possibility of her answering correctly or answering incorrectly. We're told in the question that she's got an 85% chance that the question will be about something of which she's got confident knowledge, which means that there's going to be a 15% chance that she doesn't have any knowledge on it. So we've got 0.85 and 0.15 for the first 2 branches on the tree diagram. If she's got confident knowledge about a topic, then we're told that she's got a 90% chance of answering it correctly, which means a 10% chance of answering it incorrectly. So we've got 0.9 and 0.1 as the probabilities there. If she has to guess, well, because there are 5 possible options, she's got a 1 in 5 chance or 0.2 chance of guessing it correctly and a 0.8 chance of guessing it incorrectly. To answer a question on the paper correctly, there are 2 possible routes. Either she's got confident knowledge of the question and answers it correctly, which has got probability 0.85 times by 0.9, which gives me 0.765, or she's got no knowledge of the question and then guesses correctly for that particular question, which gives me a probability of 0.15 times by 0.2, which is 0.03. So the probability that she answers the question correctly is 0.765 plus 0.03, which is 0.795. For part 2, we want the probability she had to guess the answer given that she answered it correctly. So this is a conditional probability. So we're being asked for the probability that she had to guess the answer given that she got the correct answer. So that's the probability she guesses the answer and gets the correct answer divided by the probability she gets the correct answer. If she's going to guess the answer and get it correct, it means that means she had no knowledge of the question and guesses it correctly, and that is our 0.15 times by 0.2 option, which gives 0.03, and we know the probability she gets it correct is 0.795, so we've got 0.03 divided by 0.795, which gives me 0.0392. Now, we could answer the whole of the question so far without a tree diagram, and probability of a correct answer then is the probability she's got confident knowledge of the topic and answers correctly, or no knowledge and guesses correctly. Confident knowledge has a probability of 0.85 times by 0.9 that she then gets that correct. No knowledge has got a probability of 0.15 and guesses that then correctly. It's got a probability of 0.2, so we've got 0.85 times by 0.9 plus 0.15 times by 0.2, which gives us our answer of 0.795. The probability that she guessed the answer, given that she answered it correctly, is the probability she guessed the answer and answers correctly divided by probability she answers correctly. So that's the probability she had no knowledge of the question topic and answered correctly divided by the probability she answers correctly, which is our 0.15 times 0.2 divided by 0.795, which gives us 0.0392. If 35 or more correct answers are required to pass the test, calculate the probability that Gail will pass the test. What additional assumptions were needed to find this probability? Well, we're going to have to first of all assume that the test covers all the topics in a fair way, so that 85% of the questions are on the part that Gail knows well, and that Gail doesn't get despondent if she encounters a run of questions she has to guess. And indeed, we've got to assume that Gail's estimates that she's made are correct as well. If these assumptions are valid, then we can say that the number of correct answers that Gail will get will be a binomial distribution with n equals 50 and p equals 0.795, which is the probability that she gets any particular question correct. So we want to know what is the probability that she gets 35 or more correct, and the probability that y is greater than or equal to 35 is 1 minus the probability that y is less than or equal to 34. And using the binomial functions on our calculator, we can obtain that easily. We've got 1 minus 0.0379, which gives me a probability of 0.9621. So with this level of knowledge, Gail has a 96% chance of passing the exam. Moving on to example 3, we've got a basket containing 12 red and 8 blue balls. All the balls are the same size and the same weight and made of the same material. A game consists of blindfolding a player and then asking the player to remove 3 balls without replacement from the basket. If the 3 balls are the same colour, then the player wins. First of all, we've got to prove that there's a probability of 23/95 of winning the game. Well, to win the game, we've either got to have 3 reds or 3 blues. The probability of getting 3 reds is going to be 12 over 20 times by 11 over 19 times by 10 over 18. And the probability of 3 blues is going to be 8 over 12 times by 7 over 19 times by 6 over 18. And if we work that out, that comes to exactly 23/95. After a player plays the game, the balls chosen are replaced in the basket. Michael, Saffron and Nicholas decide to take turns to play this game until somebody wins. Michael will go first, then Saffron, then Nicholas, then Michael, etc. until somebody wins. So we've got to first of all find the probability that Saffron wins on her first go. Well, it's a good idea to introduce a little bit of notation here. So what we're going to do is we'll let M with a tick denote Mike wins that go, and M with a cross denotes Mike loses his go. So if Saffron is going to win on her first go, then Mike must lose on his first go, and Saffron must then win on her first go. So we've got a probability of 72/95 that Mike loses on his first go, 23/95 that Saffron wins on her first go, so we've got 0.1835. For Saffron to win on her third go, well, what we'd have to have is first of all Mike, Saffron and Nicholas losing on their first go, Mike, Saffron and Nicholas all again losing on their second go, Mike losing on his third go, and Saffron then winning on her third go. So what we've got to have is a sequence of 7 losses followed by a win for Saffron. So the 7 losses have got a probability of 72/95 to the power 7, and then Saffron's win has got a probability of 23/95. So our probability expression is 72/95 to the power 7 times by 23/95. And that gives me 0.0348. Finally, we've got to find the probability that Nick wins the game. Now, Nick winning the game, well, he could win on his first go, or on his second go, or on his third go, or indeed on his 100th go, or even his 1000th go. So let's try and work some of these probabilities out. First of all, the probability he wins on his first go is the probability that Mike and Saffron both lose on their first go, and Nick wins on his first go. The expression for that is going to be 72/95 squared times by 23/95. The second possibility we've got is that Mike, Safi and Nick all lose on their first go, and Mike and Saffron lose on their second goes, but Nick wins on his second go. So that's 5 losses and then a win for Nick. So the probability for that is going to be 72/95 to the power 5 times by 23/95. The next term in the sequence is going to be, we've got 8 losses on the trot, followed by a Nick win. So the probability of that is going to be 72/95 to the power 8 times by 23/95. And at this stage, hopefully you'll notice that we've got a geometric progression here. And the first term in the geometric progression is 72/95 times by 23/95, and then the common ratio between the terms is 72/95 to the power 3. We've also got the sum to infinity of this geometric progression, because this game could go on forever. We know that the sum to infinity of a GP is a over 1 minus r. So in this case, we've got 72/95 squared times by 23/95, all divided by 1 minus 72/95 to the power 3. And on our calculator, that comes out to 0.2463, and that is the probability that Nick wins the game. For our final example, we've got in a large field, weeds grow at random, but at an average rate of 0.3 weeds per metre squared. The field is subdivided into squares which do not overlap of side 2 metres. Find the probability that a randomly chosen square has exactly 2 weeds growing in it. So, number of weeds growing in a square of area 4 metres squared will, provided the weeds do indeed grow at random independently of each other and at an average rate of 0.3 weeds per metre squared. In a square of area 4 metres squared, we'd expect there to be 1.2 weeds. So we're going to have x being modelled by the Poisson distribution with lambda equals 1.2. The probability that we get exactly 2 weeds growing in it then we can calculate either by using the formula, which gives 1.2 squared over 2 factorial times by e to the minus 1.2, which is equal to 0.2169, or we could even just use our Poisson functions on our calculator. For part 2, we want to find out the probability there will be 6 out of 25 randomly chosen squares with exactly 2 weeds in them. Now, provided the squares are independent of each other, which may well mean that they are well apart of each other, we should be able to say that the number of squares with exactly 2 weeds in them will be binomially distributed, with n equals 25, and p being the probability that a particular square has 2 weeds in it, which we've just calculated as being 0.2169. So we're saying that y should be binomially distributed with n equals 25 and p equals 0.2169, in which case the probability that y equals 6, we can either use the formula for working out binomial probabilities, or again we could use the binomial functions on our calculator to obtain the answer of 0.177. And that concludes our look at the process of choosing suitable probability models for discrete random variables.